In this video, I'm going to talk about energy and something new called power. We're going to talk about it in the context of a car accelerating from 0 to 60 miles an hour in some amount of time. You could take any two cars that accelerate from rest to a final speed of 60 miles an hour, which is about 27.3 meters per second, and you'd find that each car is going to take some different amount of time, right? They're designed differently, they have different masses, they've got different engines, or in the case of the Chevy Bolt, an electric motor. So if you take a Chevy Bolt, it can go from 0 to 60 or from 0 to 27.3 meters per second in approximately 6.5 seconds. Now, if you take something like a 1982 diesel Mercedes, which is something I owned about 10 or so years ago, I could go from 0 to 60. I could reach about 27.3 meters per second, but it honestly took me about 60 seconds, sometimes less, sometimes more. It depended whether there's a headwind or I was going uphill or downhill, but I could reach it, but it would take me about a minute, right? So when thinking about these two cars going from 0 to 27.3 meters per second, let's think about this in terms of energy as an introduction to this thing we call power. So when we're thinking about energy, let's imagine the system in each case is just the car, not the motor or not the engine, okay? So the first question is, throughout the acceleration, each engine or motor loses energy. Where is this energy stored in the end? So if we just include the car in the system that doesn't include the motor, with the Chevy Bolt, its batteries are losing energy, and it's using the electric motor to essentially transfer that energy to the kinetic energy of the car in the end. In the case of the Mercedes, it's losing some of the stored chemical energy in the fuel, the diesel fuel or the biofuel, whatever you're using in your diesel engine, and it's using the diesel engine to transfer that stored chemical energy into the kinetic energy of the car. So in the end, whether it's from the battery or from the chemical energy stored in diesel, this energy is being stored as kinetic energy in the end. So does one engine or motor lose more energy than the other during the acceleration from 0 to 27.3 meters per second? And why? Well, if you think about it, where is that energy being transferred to? In both cases, the battery and the motor, or the fuel and the engine, are transferring their energy to kinetic energy. And I know this is not quite true, but let's just assume for simplicity's sake that a Chevy Bolt and a 1982 diesel Mercedes has the same mass. That's not quite true, but let's just make that assumption. Well, if they have the same mass and they both reach the same speed, then both of these vehicles have the same amount of kinetic energy stored in the end, which means the motor or the engine transferred that amount of energy. They both transferred the same amount of energy because there's the same amount of energy stored in the end. Well, they're both able to provide or transfer the same amount of energy to the vehicle, but which engine would we say is the most powerful? Well, clearly the one that can transfer that same amount of energy in less time. Whichever can do the same task in less time, we would say is the more powerful engine. And that's pretty similar to how we think about it in terms of physics. The word power is something that we have a very specific meaning for, and power in physics is measured by two things. One, it's the amount of energy transferred into or out of a system, so we'll call that delta E. And the second thing that power depends on is how much time it takes to transfer that amount of energy. The equation that we use to calculate the power of something is power, or P, is equal to the change in energy divided by the change in time. If we think about the units are, if energy divided by time, it's joules divided by seconds. So the units for power are 1 joule for each second. And in physics, we call 1 joule for each second a watt. So our units for power are watts. Now think, what are other things which are measured in units of watts? Well, pretty much anything that you'd plug into an electrical outlet has a power rating. Let's think about what does that actually tell us? Let's take a microwave, for instance. A microwave has a power rating of approximately 1,000 watts. So that's 1,000 joules for each second. So that means, let's say when the microwave is on high, every second that it's on, every second that it's heating your food, it's transferring 1,000 joules of energy to it. More likely, it's just using 1,000 joules of energy each second of electrical energy from the outlet. Not all of that actually gets to your food. Okay, so it wouldn't make sense to say that the microwave uses an exact amount of energy each time, because the amount of energy it uses or is able to transfer to your food totally depends on how much time the microwave is on for. So whenever we're talking about energy problems and we want to know something about how much time it takes for change in energy to happen, we're going to have to be thinking about this thing we call power. With the Chevy Bolt, its maximum power for the electric motor is 150 kilowatts. That's 150,000 watts. So in an ideal situation, the electric motor is able to transfer 150,000 joules of energy each and every second to the kinetic energy of the car. Well, when you think about power in cars, what's another unit for power that we typically talk about and think about? It's horsepower. Horsepower is a unit of power, and the conversion between the two, watts and HP or horsepower, is this. It takes about 746 watts to be equal to 1 horsepower. So for the Chevy Bolt, 150,000 watts is about 201 horsepower. So I want to walk you through 3 scenarios to think about how you'd set up a power equation to solve for lots of different things. So scenario number 1 just has let's say an electric motor pulling a box across the floor, and let's assume that it's pulling the box at with a constant force, and let's assume the speed is constant. So there's exactly as much friction as there is tension pulling to the right, so the box moves at a constant speed. Well, if we wanted to figure out the power of the motor, power is change in energy divided by change in time. What's the change in energy of the motor? Well, remember, when a system changes energy, we'd say that work is being done. So if we can figure out how much work the motor is doing, which is the same as the positive work done on the box, we could calculate the power. It'd be work divided by time. And our general equation for work is just F times D times the cosine of theta. F is the external force a system is feeling, so let's say the constant force in the box. D is the displacement of the system while it's feeling that force, and theta is the angle between the force and the direction of motion, or the direction of the displacement. In this case, they're in the same direction, so the cosine of theta, cosine of 0 is 1, so our expression on the top is just F times D. And this is an algebraic equation which works in this situation, which we could use to solve for the power, or the force, or the distance, or the time, as long as you know all the other information in that equation. In scenario number 2, we've got somebody walking up a set of stairs. Okay, let's say the system is the person in the earth, and let's say the person starts at the bottom of the stairs, not moving. They walk up the stairs and they finish up here, also not moving, right? So did the system change energy? Well, down here they had 0 gravitational potential energy. They were at a height of 0. They weren't moving, so there's no energy stored in the kinetic energy account. When they're up here, there's still no energy in the kinetic energy account because they're not moving, but they're now higher than a height of 0. They've had some change in vertical position, so there's now energy stored in the gravitational potential energy account. And remember, it takes both the mass, in this case the person that has been raised up, and the earth to be a part of the system. Otherwise, we can't talk about a system having energy stored in the gravitational potential energy account. And so in this case, we could calculate the power of the person by taking the change in energy, which in this case is the change in gravitational potential energy, divided by the time. How much time did it take the person to go from the bottom of the stairs to the top of the stairs? Well, the top of the stairs is going to be at the same height, right? So mg delta y, this will give us how much the gravitational potential energy changed from a height of 0 to this final height. So you could have a high power rating if you're able to run up the stairs in a short time, you're dividing by a smaller number. Or if you casually walked up the stairs, you would be dividing by a larger number and you'd get a smaller power rating. The last scenario that we're going to talk about is a biker moving up an incline. Let's assume it's a smooth road, so there's no resistive friction. If there wasn't friction, the biker actually couldn't move up the road, but let's assume air resistance is negligible. They start at the bottom of the hill. We'll call that a height of 0 or a vertical position of 0. Let's say they start from rest. At some later time, they've changed their vertical position, and let's assume that they're now moving. They've got some kind of speed. So if we wanted to figure out the power of the biker, well, we've got to figure out an expression for how much the biker/earth system changed its energy. Well, like before, they've now got some gravitational potential energy because they're higher than a height of 0, but they're also moving. So in this change in energy expression, we also have to add the kinetic energy of the biker, which is 1/2 mv squared. And so kind of a little bit expanded equation would be power is equal to the mass of the biker times the gravitational field strength of the Earth times their change in vertical position plus 1/2 times the mass of the biker times their speed squared divided by the time it took them to go from position A to position B up here. So I hope you can see that this is using the general equation for power. Power is change in energy over change in time. But what we plug in for the change in energy totally depends on the scenario and what's actually given. So I hope this helps introduce this concept of power and how this relates to energy and time.